Greetings, I am Matthew Del Branson at Missouri State University, and welcome to this presentation for CSC 742, Evolutionary Computing. We'll be exploring coevolution for neural network control systems and body morphologies for soft robotics using the EvolutionGym library. So neuroevolution takes a fundamentally different approach to creating neural networks. Instead of using backpropagation and gradient descent, we evolve populations of networks using natural selection, so selecting for desired traits over generations. NEAT, neuroevolution of augmenting topologies, revolutionized the field by solving three key problems. First, it starts simple and complexifies rather than trying to optimize huge networks from scratch. Second, it uses historical markings to track innovations, enabling meaningful crossover between different network structures. And third, it protects innovation through speciation, giving new ideas time to develop before competing with established solutions. So in nature, brains didn't evolve in isolation. They co-evolved with the bodies they control. This coevolution creates a tight coupling where changes in one component will drive adaptations in the other. In this implementation, I use a single population cooperative coevolution where each individual contains both a body blueprint and a neural controller. They succeed or fail together, just like in nature. This approach can be powerful for robotics because it creates controllers that are inherently adaptable. My original ambition was to test how different NEAT variants handle robot damage and degradation. I envisioned comparing multiple implementations to see which approaches were the most robust to component failure. I quickly discovered, though, that implementing even one working NEAT system is a significant challenge. It's not just a simple genetic algorithm, the implementation challenges are pretty substantial. So it requires careful orchestration of multiple interacting systems. You have historical markings for crossover, species management for diversity, compatibility calculations for grouping. Once you add speciation, you need larger populations to maintain sufficient diversity within each species. And since each individual requires physics simulation to evaluate, then even with parallel processing, generations takes significant time to compute. And on top of all of this, parameter tuning requires extensive experimentation to find the sweet spot between exploration and exploitation. So I pivoted to focus on getting the fundamentals right first. My refined goals were to implement core NEAT with proper historical markings, speciation, and complexification. I needed to enable true coevolution where networks adapt when morphology changes. I needed to achieve meaningful locomotion behaviors before I tried to break them. And finally, I wanted to document what works, what doesn't, and why. So ultimately, rather than testing multiple implementations superficially, I chose to build just one that works well. So, this research explores three fundamental questions. First, can NEAT effectively co-evolve neural controllers alongside changing morphologies? Second, how does speciation protect innovative body-brain combinations during evolution? And third, what implementation challenges arise when evolving neural controllers for soft robotics? These questions address core challenges in evolutionary robotics. The first question tackles the fundamental problem of variable I/O. When a robot's body gains or loses sensors and actuators through mutation, how can the neural network adapt without catastrophic failure? The second question examines whether speciation actually helps in this complex coevolutionary landscape. When you have a poorly performing body paired with a potentially innovative controller, does species-based protection give it time to optimize? Or does the added complexity of managing both morphology and control overwhelm the benefits of speciation? And the third question is perhaps most important. What are the practical hurdles here? How do we handle the computational explosion when every body change requires network restructuring? What parameters actually matter when co-evolving versus evolving controllers alone? Which brings us to our testing environment. For the experiment, I am using EvolutionGym, a soft robotics simulator developed at MIT specifically for evolving robot morphologies and controllers. Unlike rigid robotic simulators, EvoGym models soft, deformable bodies using a voxel-based approach where each voxel can be one of four types. You have rigid voxels that provide structural support like bones. You have soft voxels which are passive but flexible like cartilage. You have the muscle voxels. The blue vertical muscles contract up and down. The orange horizontal muscles contract side to side. There are many tasks, too, against which you can evaluate the robots, but I chose to focus specifically on the walker task as the simplest point of entry. To track the data, I generate CSV files to log fitness statistics and species dynamics, and I generate markdown reports to track species lineages, extinctions, and breakthrough moments. Checkpoint files save complete population states, allowing me to resume runs when interrupted. My first step was implementing morphological evolution with random control, essentially testing if body shape alone could produce locomotion. In this approach, every muscle voxel fires completely randomly, sampling from the action space at each time step without any coordination or memory. Each morphological mutation targets 1 to 2 voxels determined by a Poisson distribution. When mutating an empty space, I always add a new voxel, choosing randomly between rigid, soft, or muscle types. When mutating an existing voxel, there's a 50-50 chance either remove it entirely or transform it to a different type. Critically, after each mutation, I check if the body remains connected using a flood fill algorithm. Only connected bodies survive, we can't have floating pieces. What's wild is that a random control approach is surprisingly effective. The evolutionary process discovers that aligning vertical muscles in columns creates a hopping motion. The body essentially evolves to exploit the random twitching. We see fitness scores reaching 3.68, which is not bad for completely uncoordinated muscle spasms. But this is fundamentally still a simple hill climbing problem. The body is just reorganizing to maximize the effect of random actuations. Without any sensory feedback or coordinated control, there's a hard ceiling on what we can perform here. The robot can't adapt its gait, can't respond to its current state, and can't develop sophisticated locomotion patterns. It's time to add a brain. Now I introduce neural network control, though not quite following Neat's minimal starting topology yet. At this stage, I initialize networks with 80% connectivity between inputs and outputs. That's each of 8 sensor inputs plus a bias node has an 80% chance to connect to each muscle output. If starting truly minimal, robots would lie motionless for hundreds of generations, waiting for lucky mutations to create basic connections. So I chose pragmatism over purity to get the system working. The implementation is straightforward but limited. We have 8 sensory inputs, far less than the actual voxel count. All neurons use hyperbolic tangent activation. The mutation operators are basic. Weight mutations perturb existing weights with Gaussian noise or occasionally randomize them completely. Structural mutations can add new connections between any nodes, checking for cycles to maintain feed-forward topology. Node additions work by splitting existing connections, disabling the original, and adding 2 new connections through the new node. What's pretty striking is the immediate change in movement quality. Even with these simple networks, we see more biological-looking locomotion patterns. The robots develop rhythmic gaits, coordinated muscle contractions, and primitive feedback loops. But paradoxically, the fitness actually decreases to 3.05. So why does that happen? Well, the solution space just exploded. Instead of optimizing body structure alone, we are now searching the vast space of all possible network configurations and body shapes simultaneously. This is a key challenge. Adding complexity initially hurts performance. You have to trust in the algorithm. We only had one job with random controllers, evolve a body with, that could exploit the twitching. Now these neural networks must learn to control whatever body they're given, and it's a much harder problem. Next, I implement crossover, though at this stage it is still without Neat's innovation tracking system. This is basic genetic algorithm crossover applied to neural networks, which is not ideal when parents have different topologies. Without historical markings to identify homologous genes, I make some simplifying assumptions. So for parent selection, I use tournament selection with a size of 3 to 5 individuals. The crossover itself is pretty crude. I attempt to align connections based on their positions in the genome array, essentially treating the gene list as a fixed order chromosome. This means mutations that add connections in different orders between parents can lead to misaligned crossover, but it's a starting point. Body crossover uses uniform crossover, randomly selecting each voxel position from either parent. The constraint of connectivity remains the same. After combining parent bodies, I verify the result forms a single connected component again using flood fill. If the initial combination creates disconnected chunks, I retry it up to 10 times before defaulting to copying one parent entirely. The result you see here kind of illustrates a parallel of the unsophisticated crossover approach. This robot has essentially inherited a lot of functionless body mass grafted onto another more functional lower body. The 3.26 fitness shows slight improvement over mutation alone, suggesting that even this imperfect mixing can discover useful combinations. Still, we're essentially just doing blind cut and paste operations, hoping the pieces fit together meaningfully. Now we implement Neat's most crucial component, speciation. This fundamentally changes the evolutionary dynamics by protecting innovation. I calculate compatibility distance between genomes using 3 factors: excess genes, disjoint genes, and weight differences of matching genes. Genomes within a compatibility threshold belong to the same species. Each species maintains its own representative member and competes primarily within its own niche. Here we see an early champion at 3.57 fitness. It's a powerful jumper with synchronized vertical muscles creating large bounding motions. In the old system, this design would dominate reproduction, flooding the population with only copies and variations of jumpers. But speciation, it changes everything. This peculiar robot hobbling around at 1.17 fitness would normally be eliminated immediately. It's moving differently, it's shuffling, it's crawling around, it's completely ineffective. Without speciation, it has zero chance against the jumpers, but now it's protected within its own species, competing against similar designs rather than the global champions. Given time to optimize within its niche, the crawling strategy evolves into something much better. This descendant achieves 4.18 fitness, our best yet. It discovered a more efficient locomotion pattern than the jumpers ever found. This is speciation's benefit, protecting seemingly inferior innovations long enough for their potential to emerge. We're not done yet, though. Remember, these robots still only have 8 hard-coded sensory inputs, meaning they're numb to most of their body. So here we are now with full body sensation. I implemented dynamic sensory sizing. All the voxels each provide 2 inputs, position and velocity, giving now complete proprioceptive feedback. This robot at 4.39 fitness has coordinated whole body locomotion. You can see how muscles across the body contribute to movement, creating a rippling wave pattern that travels through the body. The network has learned to synchronize contractions across multiple muscles, turning the entire structure into a unified spring mechanism. The implementation handles variable I/O by padding or truncating sensory inputs when body sizes change. If a body grows, new sensors map to 0 until evolution connects them. If a body shrinks, we simply ignore the extra network inputs. This allows networks to remain functional through morphological mutations while gradually incorporating new sensory information. The last parts of our core NEAT are finally falling into place. First, I implement gene-enable disable mutations. This allows evolution to temporarily deactivate connections without losing them forever. A harmful connection can be switched off, evolved around, and potentially reactivated later if conditions change. The enable disable mutation rate is low, around 1%, but it provides some flexibility. Secondly, I added activation function diversity. Beyond hyperbolic tangent, neurons can now use sigmoid, ReLU, or identity functions. Each hidden node can mutate its activation type with about a 3% probability per generation. It's difficult to observe the direct impact of these changes, but different activation functions should excel at different computational tasks, like ReLU neurons create sharp decision boundaries, sigmoid provides smooth switching, identity enables linear combinations, while hyperbolic tangent handles cyclic patterns. The result is our best performer yet at 5.14 fitness, and so far it's our best case of bipedal locomotion. So recognizing that available time was drawing to an end and that I'd get just one more run before this presentation, I threw every idea I could at the system. Observing previous runs, stagnation was clearly limiting progress. Champions would plateau indefinitely, and parameters that were optimal for early exploration at the beginning became counterproductive later in the end. So I built a dynamic parameter scheduler. It's a meta-evolutionary system that monitors progress and adjusts parameters on the fly. The scheduler, it has several mechanisms at play. So first, it tracks fitness progress, counting generations without improvement. When stagnation is detected, say 15 generations without progress triggering an event, or 30 generations triggering an emergency, it dramatically increases mutation power and structural mutation rates while relaxing compatibility thresholds, so it forces new species to form. Second, it has progressive scheduling across 3 different phases. We have early exploration, optimization phase, and a late-stage fine-tuning phase. So from generations 0 to 50, it uses a high mutation rate for broad search, and then when it goes on to the optimization phase, it reduces rates to refined solutions. And then in the late-stage fine-tuning, it's using minimal perturbation to just polish off the champions. And third, it has compatibility threshold dynamically adjusting every generation to maintain target species count. If we have just one species, the threshold aggressively drops to force speciation. Too many species, and it rises to encourage competition. This prevents both premature convergence and excessive fragmentation. And then finally, sinusoidal pressure waves apply to mutation power, creating like cycles of exploration and exploitation. I got the idea originally from Milankovitch cycles and other like astronomical rhythms that have been proposed to influence biodiversity through climate oscillations. And so, yeah, the result, our best performer yet at 5.61 fitness. It's still running, in fact. It's a somewhat unprincipled kitchen sink approach, but it demonstrates how meta evolution can break through performance barriers. So let's analyze what happened with our first run with the dynamic parameter scheduler. Upon first glance, I can see right away the three distinct phases. Good news first, the exploration phase from generations 0 to 50 seems to work really well. We can see the rapid fitness improvement from 0.7 to about 4.5, with the high mutation rates and structural changes allowing quick discovery of basic locomotion strategies. The species diversity graph shows healthy fluctuations throughout the run, which I suppose confirms that the compatibility threshold adjustments are maintaining multiple evolutionary niches. The opening phase was the fastest initial rise in fitness yet of all my tests, actually. But then we hit the bad, the plateau from generations 50 to 300. So for 200 generations, best fitness barely even budges while average fitness actually decreases. That's really ugly. I'm actively harming the process here. Otherwise, looking at the species count, I see explosions up to 29 species, suggesting overfragmentation, of course. Looking at my expanded reports, it looks like each species becomes too small to effectively explore its niche. And so yeah, what is happening here? I'd say during early success, high exploration parameters work because any movement is better than none. But once it transitions to the optimization phase at generation 50, the reduced mutation rates become way too conservative. The scheduler waits a whole 15 generations then before intervening, then another 30 before the emergency mode kicks in, which is why the observable changes are delayed until well after the phase shifts. And that's just way too patient when you're already stuck. Meanwhile, species management overcompensates, creating so many tiny niches that beneficial mutations can't spread around through the population. The breakthrough after generation 300 basically proves the concept, though. Eventually, emergency interventions do kick in, and it dramatically increases mutation power, forces species merging, causes aggressive structural changes, and then fitness jumps from 4.8 to 5.61, the best result yet. And so this shows that dynamic scheduling can break through stagnation at least, but ultimately my parameters need to be better tuned. My lesson learned is that parameter scheduling is tricky. You need to balance patience with aggression, diversity with convergence. My scheduler was way too gentle during optimization and too extreme in crisis. But even this imperfect implementation managed to achieve my best results, so it suggests it's at least a promising direction. I have plenty of ideas to pursue with it still, at least. Yeah, so challenges and risks. The biggest challenge was computational complexity. Each generation requires evaluating hundreds of robots for thousands of time steps over hundreds of generations. Early single-threaded runs took whole days. Multiprocessing would cut this down to a few hours, but that is still a slow development cycle, which brings me to limited time. My original proposal, I envisioned comparing multiple neat variants with degradation testing with the hope of having a programming partner and not to have to take this on alone. I was forced really to make the decision to reduce scope, building one decent implementation rather than several hasty ones. Even this simplified version was surprisingly complex, though. Parameter tuning has its own difficulties. Over 20 parameters, compatibility thresholds, mutation rates, species targets, all interacting in nonlinear ways. Too much structural mutation and networks would become tangled, too little and they stagnate. On every stagnant robot's video, you can see the obvious perfect changes to one or two voxels that would send the species into instant success, but you just have to keep pulling the slot machine hoping to stumble into it instead. After weeks of manual tuning, the dynamic scheduler was really helpful. The cost of mistakes became painfully clear too when a bug in speciation logic wasted 3 days of compute for me. My solution then afterwards was to recruit spare computers I could access, so my laptop, a desktop, and several borrowed machines all ran different parameter sweeps in parallel. So in conclusion, I was able to implement NEAT from scratch, achieving coevolution of both neural controllers and soft robot bodies. It demonstrates how speciation protects innovation. The implementation itself is clean, modular, providing a solid foundation for future expansion. I was able to show how each NEAT component plays a role in evolving sophisticated behaviors. The progression videos make visible what's sometimes hard to see just from the fitness graphs. Additionally, the dynamic parameter scheduler, while it's still rough, it demonstrates a promising approach, I think, to the perpetual parameter tuning problem. Looking forward, the immediate priority is parameter refinement. The scheduler needs more aggressive stagnation intervention, dropping from 15 and 30 generation patients probably down to 5 and 10. Species management should be gentler, and phase transition should really respond to actual progress rather than fixed schedules. Next, I would also be implementing true minimal topology initialization. So my pragmatic 80% connectivity got quick results, but neat's elegance really comes from growing complexity from almost nothing. My expectation, too, is that I can achieve higher scores if dedicating the time to that. Walking is just the beginning, too. There's climbing, jumping, carrying, many more. Success across domains would prove true robustness, not just task-specific optimization. HyperNeat represents the natural evolution of this work, encoding geometric patterns. This could enable scaling to much larger bodies while maintaining coherent control patterns. And I can pursue the original vision, which was systematic degradation studies. This would conclude at least what I initially wanted to complete. So thank you for listening. Take care.